Hello and welcome to Pharma-info with Shubhashish. Now today's topic is pyrimidine, right? We know that pyrimidine is found to be one of the important nitrogenous base, okay, which basically constitute our genetic materials and all, right? So it is the DNA for which the building blocks are found to be the nitrogenous base, and we have three bases, 1.1 to RNA, and the next two is for DNA, right? So we know about adenine, guanine, thymine, cytosine, okay, and uracil as well. Fine. So it is the uracil, thymine, thymidine, at the same time cytosine, right? These three are the the nitrogenous base in which the pyrimidine ring is important. So so instead of focusing on the medicinal uses, right? So without this, okay, our genetic material will not get produced. So here comes the importance of this particular ring, right? So without wasting time, let's just draw the structure of pyrimidine. So pyrimidine is the one in which nitrogen is present as a heteroatom, right? It is a six-membered ring system, right? Six-membered ring system, and it looks like this. Fine. So this is about your pyrimidine. So if I just replace this nitrogen with the carbon, so what will happen? It turns out to be pyridine. So it is pyridine for which the third carbon is replaced with a nitrogen. That means it is as similar as that of pyridine or benzene, right? Only thing is that we are replacing carbon with nitrogen, or we are putting multiple nitrogens like this. Fine. So here from where we are supposed to start the numbering, any of the nitrogen. So preferentially this one. Fine. So this is found to be the 1, the position 1, this one is 2, this one is 3, this one is 4, this one is 5, and this one is 6. Fine. So this is how the numbering goes. So with that we are done with the numbering of pyrimidine. Fine. As I said, pyrimidine is found to be one of the, make sure please don't forget that pyrimidine is found to be one of the important nitrogenous base, the essential building block, or we can say the central body of the essential building blocks of DNA. Fine. Chalo, now the thing is that, so let's do one thing. Let's just find the ways by which pyrimidine can be synthesized. Fine. So you might have studied, okay, or you are going to study barbituric acid derivatives, right? Barbituric acid derivatives. Fine. So barbituric acid is what? Barbituric acid is, if I just write the structure of barbituric acid, those who are who are watching this video, or who are watching this video, okay, if they have started their medicinal chemistry journey, right? They might have might have with them the information about the barbituric acid derivatives, because it is acting as a sedative hypnotic, right? So this is found to be the skeleton of barbituric acid. Fine. So this is found to be, okay, we have two more carbonyl, right? Carbonyl, and finally we have CH2. Fine. So this is all about here. So it is as similar as that of pyrimidine. Only thing is that the oxo, this oxo, 1, 2, 3, 3 oxo are there. Fine. So this is called as barbituric acid. So see how nice this one is. If I just split or isolate our barbituric acid from this end, from these two portions, right? We are basically left with what? Two different fragments. If I complete each and every fragments, this is as similar as that of urea, and this is as similar as that of malonic acid. So it's basically an amalgamation, or we can say it's basically an union of malonic acid as well as urea, that eventually give rise to the formation of what? Barbituric acid. So barbituric acid is nothing but a derivative of what? Derivative of pyrimidine. Fine. So this is the one that is found to be the starting material of pyrimidine. Fine. So let's do one thing. Let us just just rotate this one. Fine. For the convenience of presentation, let me do one thing. Let me just orient this one in a vertical way, right? In a vertical way. Okay. So the trivial name of this particular system is barbituric acid, right? Barbituric acid. What about the IUPAC version, right? What about the IUPAC version? IUPAC version says that barbituric acid is nothing but, it's basically a saturated one. Fine. It's a basically saturated one. So this is having what? This is having two nitrogen, and nitrogen is nothing but aza. We know that nitrogen can be termed as aza. Fine. And since this one is a 6-member system, obviously we need to introduce IN. Fine. And it's the saturated one, that means N should be there. Fine. So these are found to be the common syntax, what we can say, right? once we find some time, then I'll just make a video on this, the nomenclature of heterocycles, right? Heterocycle, that is one of the important, the fundamental of heterocyclic chemistry, right? Fine. So this one is ASA, this one is IN, this one is N, right? ASA means it talks about nitrogen, IN talks about 6-membered system, N talks about whether the system is saturated or unsaturated, fine. So this is all the information that we are going to get, right? As I said, okay, if I find some time, definitely I'll make a video on this, the nomenclature of heterocycles, fine. So now the thing is that this can be called as what? This can be called as, this is basically, diagenane, what we can say, right? So what are the locations? So this is one, this is, as I said, 1, 2, 3, 4, 5, 6. So here it is the second position, this one is the fourth position, this one is the sixth position, fine. So thus we can write like, this is 1, 3, diagenane, right? Diagenane, 2, 4, 6. And but the thing is that what about the oxo? Fine, we can call it as like 2, 4, 6 trioxo, or we can say 1, 3 diagenane, 2, 4, 6 trione, diagenane, 2, 4, 6 trione. If we are using like 2, 4, 6 trioxo, 1, 3 diagenane, तब भी चलेगा. अगर आप ऐसे लिखते हो कि 1, 3 diagenane, 2, 4, 6 trione, तब भी चलेगा. Fine, चलो. So now the thing is that, so here is its own as well. This is basically a cyclic amide, right? So that is why it is highly susceptible towards what? Towards tautomerization. So it is because this is the the arrow which basically represents what? Tautomers, right? So if it undergoes tautomerization, what will happen? No longer it remain as oxo, rather inside the ring you must find what? A pi cloud. Okay, pi cloud. Chalo. So I am not supposed to write like this. So the double bond, if I just put double bond inside the ring, what will happen? The valency will not get satisfied. So thus we can say this will remain as hydroxyl. So this is not the way, this is not the way, this is not the way. Rather, what is the way? The way is, I am not supposed to write in this way because the double bond is there, fine. And this double bond came out of what? Out of exchange only, fine. So likewise, so this is found to be the wrong way. So what is the right way of writing this? So this is like this. If I just put the double bond, endocyclic double bond, so what will happen? They will get converted to hydroxyl because we know about keto-enol tautomerization. So earlier it was keto, now it turns to enol. So this is in, this is all, fine. So this is found to be the right way, fine. So this is out of tautomerization only it acquires this kind of form, right? And once it acquires this kind of form, what will happen? I need to treat this with POCl3 because it is the POCl3 that is basically replacing what? The hydroxyl with Cl. Our ultimate objective is to develop pyrimidine, not barbituric acid or trihydroxypyrimidine, fine. Rather we need to eliminate what? We need to eliminate the hydroxyl group. The best way to eliminate hydroxyl group is to convert the hydroxyl initially to a trichloro, that I am after. So on treatment with POCl3, phosphorus oxychloride, so what will happen? It is the phosphorus oxychloride that is basically chlorinate what? The areas where hydroxyl groups are there, fine. So these are found to be the hydroxyl group. So in place of hydroxyl group, what will happen? This hydroxyl will no longer be there. Why? Because this has already been treated with what? POCl3. So what will happen? Instead of hydroxyl, chloro and chloro will come, right? So, and the double bond should be there inside the ring, fine. So this is how, so no hydroxyl because I am treating this with POCl3. Once I am treating these things with POCl3, what will happen? The hydroxyl will no longer exist, fine. Thus the hydroxyl will be replaced with chloro, fine. So this is not the way, you are not supposed to write, this is for your understanding only. I just wrote in this way and later on I just convert it, fine. So this can be written as, this can be drawn as in a fresh way. How this can be drawn? This can be drawn in this way. So if I just write like this, chloro and chloro, right? Fine. So this is the way. So thus we got what? Thus we got trichloropyrimidine. Now what is left in the process? Only thing I am left with is just removal of chloro. And how this can be done? You need to introduce what? Zinc dust. For this very purpose, you need to introduce zinc dust, and of course hot water is very much required over here. Hot water, fine. So what will happen as a result of this treatment? What will happen? There is a formation of what? Unsubstituted pyrimidine occurs. Fine. So thus we are done with what? The pyrimidine. Right? So with that we are done with what? The first way of making pyrimidine. So what I did initially I have taken barbituric acid. Barbituric is the same thing, barbituric acid. It is the barbituric acid that is basically undergoing what? Tautomerization. Tautomerization, right? It is through tautomerization what we got? We got trihydroxypyrimidine, fine. It is the trihydroxypyrimidine on treatment with POCl3, phosphorus oxychloride, produced what? Produced trichloro. This is 2,4,6 trichloro pyrimidine, right? This on treatment with zinc dust, hot water will give what, or will produce what? The compound of interest, that is pyrimidine. So this is how the process stands. Hope you understand, okay, what I am delivering here. So now let's do one thing. Let us just bring another way by which pyridine can be produced actually. Okay. Now the other way by which pyridine can be produced is a simple one-step reaction, right? One-step reaction. So here we are basically taking a derivative of pyrimidine. This is another way. So this is synthesis 2 of pyrimidine. Fine. So what is the way? The way is, do one thing, you just take pyrimidine and make it a derivative of pyrimidine, right? Derivative. So this is the derivative of pyrimidine. So what is that? This is position 1, 2, 3 and 4. So thus we can write here 4-methyl pyrimidine. It is the 4-methyl pyrimidine that need to undergo what? Oxidation. Fine. It is through oxidation this will get converted to what? Suppose I am performing here, I am expecting that this will undergo oxidation, right? So it is the oxidation that will produce, that will convert this CH3 into COH, fine. So once I get COH, that should undergo what? Decarboxylation, fine. So once this CH3 is getting converted to COH, what is left in the process to make it a unsubstituted pyrimidine? Decarboxylation. It is the decarboxylation that eventually gives rise to the production of what? Pyrimidine. Right. So likewise, I can just write here oxidation followed by decarboxylation. Right. So what will happen? This is one of the simplest way by which pyrimidine can be produced, right? So this is found to be like this. So thus I got what? Pyrimidine. This is another way by which pyrimidine can be produced. So hope you understood, okay, what I taught in today's session, right? So this is the first way I explained, okay, a few minutes back, right? This is the first way, right? And then we moved on to the second way, right? That is the other synthesis 2, that is 4-methyl pyrimidine while undergoing oxidation followed by decarboxylation produced what? Pyrimidine. So hope you understood, okay, the in detail explanation of the synthetic way by which pyrimidine can be produced. So please put your valuable comments and let me also know that what are the shortcomings or what are the positive part of this particular video. Please put your comments. Your comments are important for both of us to grow. So thank you. See you on my next video.